December 1984. Edwards Air Force Base, California. A strange aircraft sits on the runway. Its wings bend the wrong way. Every pilot who saw it asked the same question. Is that wing on backwards? It wasn't a mistake. It was one of the most radical experiments in aviation history. A wing so unstable, only a computer could keep it flying. A design so extreme it still divides engineers today. What if this wing hadn't stayed an experiment? What if forward-swept wings had become the new standard for fighter jets? Would air combat look completely different today? Or was this design always doomed to remain a curiosity? To answer that, we have to go back to where this idea began. Not in the 1980s, but decades earlier. The forward-swept wing wasn't new. German engineers experimented with it during the Second World War. The forward-swept design promised better low-speed handling and resistance to stalling at the wingtips. But there was a fatal flaw. At high speed, the wing wanted to twist and tear itself apart. Engineers called it aeroelastic divergence. Push the wing too fast and it would twist until it failed. For 30 years, the forward-swept wing was considered a dead end. Metal simply wasn't strong or light enough to survive it. Then, in the 1970s, a new material changed everything: composite fiber. Unlike metal, composite material could be engineered to bend in one direction while resisting twist in another. This technique had a name: aeroelastic tailoring, and it promised to solve the forward-swept wing's oldest problem. In 1977, the Defense Advanced Research Projects Agency, DARPA, launched a bold new program. Their goal? Build a fighter-sized aircraft to prove forward-swept wings could finally work. Grumman Aerospace won the contract, beating out other major defense contractors for the chance to build the impossible wing. The project was designated X-29, a new chapter in America's experimental aircraft program. To save money, engineers reused existing parts: an F-5 CAF fuselage, F-16 landing gear, and flight control hardware. But the wing itself would be built entirely new, from graphite epoxy composite, layer by layer. 2 prototypes were built. Each one would push aerodynamic theory further than any aircraft before it. The X-29's wings swept forward at 33 degrees, the opposite of nearly every fighter jet in history. Small canard fins sat ahead of the cockpit, working with the wing to control the aircraft's pitch. The aircraft was deliberately built unstable. In the air, it wanted to tumble out of control at every moment. This was called relaxed static stability. It made the plane incredibly agile, but impossible for a human to fly alone. The solution was a triple redundant digital fly-by-wire computer system, making corrections 40 times every second. If all 3 digital computers failed, a backup analog system stood ready to bring the aircraft home. This combination of composite wing and computer control was the key. Without both, the X-29 could never fly. A third lifting surface, called the strake flap, sat at the rear, giving engineers a third axis of control. 3 control surfaces working together: canards, wing flaperons, and strake flaps. A configuration never attempted before. December 14th, 1984. Test pilot Chuck Sewell climbed into the cockpit for the X-29's first flight. Engineers held their breath. No one truly knew if the computer could control a wing built to be unstable. The X-29 lifted off the runway. For the first time in decades, a forward-swept wing fighter flew. It flew straight and true. The composite wing held its shape exactly as engineers had calculated. Einstein had calculated. Over the following months, test pilots slowly expanded the flight envelope, pushing speed and altitude step by step. The aircraft eventually flew past the speed of sound, proving the composite wing could survive high-speed stress. Then came the most extreme tests of all: extreme angles of attack, where the aircraft's nose pointed skyward while still flying forward. The canards and computer kept the aircraft controllable even past 60 degrees, angles that would send most fighters into a spin. 2 X-29 aircraft flew a combined total of nearly 600 test flights between 1984 and 1992. Remarkably, in 8 years of extreme experimental flying, neither aircraft was ever lost. The X-29 was never meant for combat. It existed purely to answer engineering questions. NASA took over research flights in the later years, studying handling qualities and high angle of attack aerodynamics. Dozens of test pilots and engineers built an enormous body of data on unstable forward-swept flight. Won its end. By 1992, the program had achieved everything it set out to prove. The aircraft was retired. Today, the 2 X-29s rest in museums, silent monuments to one of aviation's boldest experiments. The X-29 proved that composite materials could finally tame the forward-swept wing's oldest enemy, aeroelastic divergence. It also proved digital fly, by-wire systems could safely control an aircraft that was aerodynamically unstable by design. These lessons quietly influenced later aircraft, even ones that never had a forward-swept wing at all. But despite its success, the forward-swept wing never entered mainstream production. The reasons were practical, not aerodynamic. Cost, maintenance complexity, and stealth requirements all worked against it. The wing worked. The military math didn't. This is where our story shifts. Everything from here forward is speculation, not history. A realistic look at what could have been. Imagine if, in the mid-1990s, the Air Force had greenlit a production forward-swept wing fighter based on X-29 lessons. Engineers would have needed to solve one more problem: making the composite wing structure light enough for mass production. In this scenario, a hypothetical aircraft, call it the F-23Fs, emerges as a lightweight air superiority fighter. In this alternate timeline, the forward-swept wing's agility would have been a dogfighter's dream at low and medium speeds. Pilots would gain incredible control at high angles of attack, useful in close-range combat maneuvers. But realistically, the same composite technology that saved the wing would have driven maintenance costs sharply upward. Any damage to a composite wing requires specialized repair, unlike the simple sheet metal patches used on traditional aircraft. There's also the matter of stealth. Forward-swept wings create radar reflection angles that clash with stealth shaping principles. By the late 1990s, stealth was becoming the top priority for air forces worldwide. This would have worked against our hypothetical fighter. Realistically, our alternate fighter would likely have remained a specialized aircraft, not a mainstream replacement for existing fighters. A niche interceptor or aggressor trainer perhaps. Valuable but never dominant across the entire fighter fleet. Today, thrust vectoring engines give modern fighters much of the agility forward-swept wings once promised, without the aerodynamic penalties. Modern composite manufacturing has also advanced far beyond what Grumman engineers had access to in the 1980s. Digital fly, by-wire, once experimental on the X-29, is now standard on virtually every modern fighter jet. Yet even now, no major air force has returned to the forward-swept wing for a frontline fighter. The closest modern relative is Russia's Sukhoi Su-47 Berkut, another forward-swept wing demonstrator that also never entered production. Its story mirrors the X-29 almost exactly. Brilliant engineering, real performance gains, but never a path to mass production. So, would forward-swept wings have become standard if the X-29 had gone further? Realistically, the evidence says no. The wing solved one problem, structural divergence, but created new ones in cost, stealth, and maintenance that never went away. But calling the X-29 a failure would be wrong. It succeeded completely at its actual mission, proving what was possible. Every fly, by-wire fighter flying today owes a small debt to the lessons learned from this strange, backward-winged aircraft. The Grumman X-29 never fought a single battle. It never carried a weapon. But it changed how engineers think about flight. Sometimes the most important aircraft in history are the ones that never went to war at all. Today, it sits in a museum, wings bent the wrong way, still asking the same question it always did.